Can you see it now?
Yes.
You can. Yeah?
Yes, we can.
Okay. So I can start now. So thank you, Roberto, for the introduction, and thank you very much for the invitation to speak at this Italian Physical Society Colloquium. Even though it's a virtual colloquium, I'm very pleased to be here. And so thank you again. So let me start. So today I'm going to talk about extreme value statistics. So this is a subject that we have been working for the last few years, many years, in fact, and you know, it's a subject I like because it has a lot of interdisciplinary connections and applications, as mentioning, and in particular on one side, physics and statistics, and all the way up to engineering and even climate studies and so on. So it's very, you know, I find it a very exciting subject. So today I'm just going to, I mean, I won't go into the details since it's a colloquium. I'm just going to give an overview and some perspectives on this problem, that what are the basic problems and what are how we approach this problem. So this will be just an overview and perspectives. Okay, so let me start. So extreme events like earthquake or, you know, tornado or typhoon or even the COVID-19 pandemic that we are going through right now. So these are, of course, you know, rare events. They do not happen every day, but when they happen, and if they happen, their effects can be devastating. And so it's obviously very important to know the magnitude of such extreme events or the times at which they can occur and things like that. Okay, so this is a sort of very basic questions of interest. And in fact, the extreme value statistics has been studied for a long time, mostly in the statistics literature, with many applications like climate studies, finance, economies, hydrology, sports, and so on. But of late, you know, more recently, it has been found that even in physical systems like physics of disordered systems or random walks, random matrices, and so on. So there's more and more applications of these extreme value statistics. So as you will see in the rest of the talk, and so this is this sort of interdisciplinary nature of the subject, which I find it interesting. So let me just show you some applications of it, starting with a very practical engineering applications. Sorry. Hello? Hello? Yeah. Okay. So imagine that, okay, so this is a very sort of practical engineering question. So imagine that you are an engineer and you are supposed to build a bridge over a river. And what you have at your disposal is the average height of the river water level for the last many years. So for example, in this picture, what you see is the height of the Nile River near Cairo for almost 600 years. And so you have this data of the water level and you want to build your bridge. Now you can actually look at the time average, which is shown by the bold line here, and you want to you might want to build a bridge above this average height, but that is actually not much concern to you, because I mean what you really care about are these objects, these outliers or these spikes in this time series data, which means so this is suddenly the river height has become very high, and this is because of flood and things like that. So this is an outlier, this is an outlier. So these are the extreme events. And so if you are an engineer, I mean, what you really care about is the typical value of such spikes, basically. So you want to build your bridge higher than these typical values of these spikes, not the average value. Okay. So obviously what you are therefore interested in the magnitude of these extreme events, typical value of these extreme events or their statistics and so on. And it's very important for you to construct your bridge, essentially. And similarly, I mean, if you look at the if you look at, for example, the data for the time series data for the river, for the rainfall or even temperature time series, what you see is that there is spikes here, these spikes which are much more than the average, and these are the sort of rare events which contribute to the extreme fluctuations, and therefore are very crucial to understand. For example, in the global warming, you want to know these record temperatures or fluctuations which cause the global warming, and so this understanding the statistics of such events, their magnitude or their frequency, is extremely important for any of these time series analysis. Okay. Now let me give you an example from physics now. So this is the physics of disordered systems. So imagine that you have a quantum system with some Hamiltonian H on a lattice. So I can always write down this Hamiltonian in the matrix form, Hij, Ij. So this is in the side basis. So I can always express the Hamiltonian like this. Now, when we say a system is disordered, that means this quantum, this matrix Hij, which is the Hamiltonian. So this has disordered elements, and so it's in general this is the Hermitian matrix, and so we want to make the matrix elements random to model a disordered system. Now, how you are going to choose the elements of your matrix, that depends on the model you want to look at. For example, if you just take the nearest neighbor interaction on your lattice, then this matrix will have only tri-diagonal elements, diagonal and the two off-diagonal elements. Rest of the elements will be 0 because this is a nearest neighbor interaction. And then this is the famous Anderson model of disordered system. On the other hand, if you are looking for a mean field system where every site is connected to every site, the matrix is full. And in that case, if you choose the matrix elements from independently from a Gaussian distribution. So the joint distribution of the matrix elements is just the product of the Gaussians, which you can write as exponential minus trace of H squared. And this particular choice of the entry distribution has played a very crucial role. This is called the Gaussian unitary ensemble. Why is it called Gaussian unitary ensemble? Because you see the joint distribution of the matrix elements, because you write as a trace of H dagger H. So if you make a unitary rotation, if you change your basis, then obviously this measure is going to be independent of the basis. And this property actually helps you to compute many objects in this random matrix literature. And therefore, this plays a very central role, this Gaussian unitary ensemble. But basically, the point is that, okay, whatever your model is, you have a Hamiltonian and you choose your matrix elements from some distribution. And then you diagonalize this matrix and you get the n real eigenvalues. And they are typically very strongly correlated. And what you want, for example, to a typical quantity of interest is the ground state energy, which is the minimum of these eigenvalues. Okay, so this is your ground state energy, and of course, this ground state energy is going to fluctuate from one realization of the matrix to another. So it's a random variable, and understanding the statistics of E0 when you vary your disorder is one of the central problem in disordered systems. And not just the ground state energy, you can ask what is the next excited state, which is the next largest eigenvalue, or the third excited state, or the gaps between them. All these questions are of interest in disordered systems, and so extreme value statistics plays a very, very crucial and central role in disordered systems. Okay. So here are these examples. So all these examples in a general setting. So what is the general setting? So general setting is the following. So basically, what you have is a time series x1, x2, x3, xn, for example. Okay, it can be any time series. It can be rainfall, temperature, or height of a river, or stock price, or whatever you want. And generally, these random variables, the entries of your time series, or you can actually, if you think of a disordered system, you can think of this as lambda I versus I. So lambda is just ith eigenvalue, and you're just plotting them as a function of I. And so these entries, these of your time series x1, x2, x3, xn, they are distributed in some way, which you may not know what the underlying distribution is, but there will be some joint distribution. They may be correlated, they may be independent, but this depends on the modeling. So whichever system you want to model, you have to have some idea of this joint distribution of these underlying elements. Okay, and then once you have this joint distribution, so this is the part of modeling. And once you have this joint distribution, then from this joint distribution, you want to calculate several extreme value observables. For example, you might be interested, from your data, from your sample, you just look at the maximum one, x max, so the value of the maximum one, which is the maximum of x1, x2, x3, xn, or the minimum one, minimum of x1, x2, x3, xn. So you can ask, given this joint distribution P of x1, x2, x3, xn, what can I say about the statistics of x max or x min? Okay, so this is a computation part. So this is the modeling part where you have to, from your data, you have to build up some model for the joint distribution. And then the second part is the statistical physics part, which is the computation part, that given this joint distribution, what can I say about the extreme observables like x max or x min? And it's not just x max or x min. There are other extreme value observables. For example, you can ask, what is the time at which the maximum occurs, the T max, or what is the time at which the minimum occurs, which is the T min. So statistics of T min or T max, or the order statistics. For example, you can ask not just the x min, But what about the second, or the global maximum, but the second maximum, third maximum, fourth maximum, etc., or opposite side, that is the ground state energy, or the first excited state, second excited state, the gap between them. So these are called order statistics. Okay, and then there's the other object which has been studied quite a lot, which is called the record statistics. So what is record statistics? So record, as you know very intuitively, so you have your time series. And so the red dots are records. So record means that a record happens at step K if the value there exceeds all the other previous values, right? We say a record happens, record temperature means that it has never happened before. So the XK, if it exceeds all the previous values, then we say that a record has happened at step K. So you can ask, okay, I give you this time series, and you can take any time series, and you can compute very easily the number of records, Mn, which is a random variable. So you can ask, what is this statistic? How many records occur in a time step n? Okay, so if I give you this joint distribution P of x1, x2, x3, xn, then can you tell me what is the statistics of the number of records? Or you can ask about the ages of records. By ages of records, I mean that if a record happens, it remains a record for a certain amount of time, and then it gets broken by a new record. So this is the age of the record, that is how long it remains a record. Okay, so how long does the record survive? So you have the statistics of this L1, L2, L3, L record statistic, age statistics of the records, and so on. And this has been actually, these record statistics have found a lot of applications, obviously in sports and evolution models in biology. Then disordered systems like spin glasses, avalanches, growing networks, global warming, many applications. But basic questions are these. You give me this joint distribution. Can you calculate the statistics of Mn, or statistics of the ages of the records? Okay. So this is the general setting. Okay. So you have this, you give me from your model, you find out what, you build a model for this joint distribution. And then as a statistical physicist, you want to compute the statistics of the maximum, minimum, the time of their occurrences, their record statistics, order statistics, and these are the general questions. Okay, so this is the sort of very general problem that is main questions that we address in extreme value statistics. Okay, so now let me start with the simplest classical model that have been studied for many years. So what is the simplest classical model? So the simplest classical model is when these variables of your time series, the entries x1, x2, x3, xn, they are completely independent. There is no correlation between them. Okay, so you can write this joint distribution factorizes into the product of the individual distributions. P of x, little p of x, is the distribution of each variable independently. Okay, so they are totally uncorrelated. So for example, in the context of disordered system, you can think of this x1, x2, x3, xn. So it's like the Hamiltonian that I showed you, the n by n Hermitian matrix. So imagine that this matrix is completely diagonal, and the diagonal elements are just the energy levels, and we assume that these energy levels are totally independent. And this is the famous random energy model of Derrida, which has played a very important role in understanding disordered systems like spin glasses and so on. And so this is the simplest example, that when the variables are uncorrelated. Okay, so in this case, so all the extreme observables that I talked about, namely the distribution of the x max or x min, or the distribution of time T max and T min, and order gap statistic, record statistics, all these things can be computed explicitly. Okay, I'll not go into the calculation of the extremes. I'll just show you how to compute the distribution of x max, just to give you an idea. But all these things can be computed when there are no correlations between these events, between these variables. Okay, so let's just to see an example. So suppose that you give me this joint distribution which is factorized. So you give me this little p of x. This is your input, and I want to compute the distribution of the maximum of these values x1, x2, x3, xn. Okay, so how do I compute this? So for this, the object which is sort of which allows us to calculate this is actually cumulative distribution of x max. Why? Because if I define the cumulative distribution, that means I ask what is the probability that the maximum value is less than some given w. Okay, so I call it qn of w. This is the central object. Now, if the maximum is less than equal to w, which means necessarily that all the elements should be less than w, right? Because their maximum is less than w, so clearly all of them have to be less than w. So therefore, what you see immediately is that this object, because they are uncorrelated, so this object factorizes, as I said. So using this factorization rule, immediately see this is just probability that any one of the element is less than W to the power n. Okay, so it's very simple. And of course, this you can write as 1 minus W to infinity, just using the normalization to the power n. Why you want to do that? Because this is useful for doing the asymptotic analysis. Okay, so this is so you give me P of X, and then I can tell you exactly, this is an exact answer, valid for any W, any N, okay? But then as a physicist, of course, you want to know, okay, this depends on the details of this P of X, of course. So one question is that, is there any sort of, as a physicist, you're always looking for universalities. Are there any universality, in particular when N becomes large, okay, where this somehow this distribution does not depend on the details of P of X, okay? Like, for example, in central limit theorem, we know that if you take a set of independent variables and if you look at their sum, then under certain conditions, that the sum is usually always given by Gaussian distribution in the large N limit. So this is a statement of central limit theorem. So similarly, we can ask, is there any analog of central limit theorem for the extreme value distributions? Okay, then the answer turns out to be yes, indeed there is. And so I take N to be large, and W to be large, and then what happens is that you can write down this cumulative distribution Qn of W as a scaling form, some function of W minus An and Bn. So this is the centering and this is the scale. So this An and Bn, they do depend on the details of P of X, but it turns out that the scaling function is universal, and it has only 3 possible scaling functions. Okay, so these are the laws of extremes. And these scaling function, there are 3 scaling functions that depend on the tail of your input P of X. Okay, so on the generic tail of Px, but it's otherwise independent of the details of the P of X. So these are the law, the analog of the central limit theorem, and this was worked out almost 100 years back by Frechet, Fischer, Tippe, Nedenko, Gumbel, and so on. And it has, as I said, it has many applications, including in the random energy model of Derrida. And so what are the three scaling functions? So this is just a detail, but okay, so that depends on how P of X, your input function P of X, the tail of P of X is. So if the P of X is unbounded and it decays faster than any algebraic law, for example, exponential or Gaussian, etc., then it turns out that f1z has a simple form which is called the Gumbel distribution, exponential of minus e to the power minus z. If it has a power law tail, then you have a slightly different form which is called the Frechet law. Details are not very important. You will see a picture immediately. And if P of X is bounded, like for example uniform distribution over 0 and 1, then you have another form which is called the Weibull distribution. So if these are cumulative distributions, so if you take the derivative of them, which are the PDFs of this maximum, so these are the 3 possible curves. So Gumbel, Frechet, and Weibull. Okay. So these are the 3 possible limiting distributions. So the point is that no matter what the P of X is, as long as you tell me what the tail of the P of X is, Nedenko's theorem tells you that there are only 3 possible fixed point functions. Okay, this is like the renormalization group in statistical physics, that there are only 3 fixed point functions. You cannot have anything else. Okay, for a generic P of X, okay? You will fall into one of the 3 universality classes. And so this is very nice, and we are very happy that this is, we can say, something about the limiting fixed point distributions. Okay. Now, what happens in most of the practical situations, however, is that the underlying variables are correlated. Correlated means that the joint distribution does not factorize into individual marginal distributions. Okay. So then, of course, the extreme value statistics is highly non-trivial, because we can no longer use this factorization property and use this nice, nice three functions of independent variables. Okay, so what do we do then? Okay, so this is the problem. Okay, what happens in the presence of correlations? Okay, now you can make a quick progress in the case when the correlations are weak. By weak, what I mean is that suppose that these objects are correlated, but there is a typical correlation length of psi, which is of finite, of order 1, and it's much less than your size of the system n. Okay, so in that case, you can use the basic idea of Kadanoff kind of idea of block renormalization. So what you can do is you can take your time series and you break it into blocks of correlation length psi. Okay, now what it means is that inside the block, these variables are strongly correlated, of course, but across the block, they are uncorrelated because this is the correlation length. So beyond which they are uncorrelated essentially. So then what you do it in 2 steps. So first, you look at inside your block, and from this block, you find out what is the local maximum in that block. So let's call it Zi. So Z1 is the maximum of the first block. Z2 is the maximum of the second block, shown by blue here, blue dots. Okay. But I don't know how to calculate the distribution of the Zi. But all I know is that the Zi variables, they are block maximum and they are uncorrelated. Okay. So then, even if I don't know what the distribution of Zi's are, point is that I'm looking for the global maximum, which is the maximum of Zi variables. So Zi's are, I don't know their individual P of Z, but all I know is that they are independent. So I can again use the independent variable theory, and in fact, you see that whatever be the individual distribution is, I know that I can get an idea by numerically computing the distribution of the maximum, and I know that it still tells me that the global maximum will be either Fréchet, Gamble, or Weibull, because the Zi variables are essentially uncorrelated. Okay. So for weakly correlated variables, we still can get an approximate theory. Which is just by this kind of RG ideas. Okay. So unfortunately, what happens when these variables are strongly correlated? That means when this correlation length is of the order of the system size. Okay. So in that case, the extreme value statistics is very hard, and we don't know any theory. Okay, so this is the and there are very few exact results, and so this is the limit that I'm interested in for strongly correlated random variables. So this is our main interest, that what can we say about the extreme value statistics in strongly correlated systems and at correlation length. Okay, and you'll see many examples of this as in the rest of the talk. So this is the problem I'm interested in: extreme value statistics in strongly correlated systems. Okay. So in the rest of the talk, I'm going to talk about this only, okay, this strongly correlated system. So what is the key idea? Before I go into the many examples, I just want to give you a sort of very basic key idea. And once you have that, then you sort of realize what you do. Okay. So what is the key idea? So the key idea is to somehow use the standard tools from statistical physics. So how do we use these tools? So again, I have, let's say, I'm looking for the maximum of a set of random variables, which are drawn from some underlying joint distribution. Okay. So, and they are not factorizable in general. So as I said, the key object is to look at the cumulative distribution, QNW. So what is the probability that the X max is less than or equal to W? So as I said, this is exactly same as the probability that each of these guys is less than W. Okay. But unfortunately, now I cannot use factorization. But nevertheless, so if I know the joint distribution P of x1, x2, x3, xn, this is just a multiple integral, right, which is going from -infinity to W, each of the variables, and I have this joint distribution. Okay. So the idea is that, okay, you can always write this P as e to the power minus e, okay, where e is just log minus of log P. I'm just rewriting P as e to the power minus log, e to the power log P. Okay. But then I can interpret this as a Boltzmann weight, and this is just a partition function of a gas of particles whose gas of n particles whose positions are x1, x2, x3, xn, and the only constraint is that they are constrained to be less than W. So that means as if there's a hard wall at W, and you have a gas of particles whose energy is given by your P you have given me from your data, and so all you have to do is to compute this partition function in the presence of a wall. Okay, and once you have that, then you have the idea of what is the distribution of the maximum. So this is the key idea. And partition function, of course, we know from equilibrium statistical mechanics, we have all kinds of techniques to compute the partition function, and therefore, we can use the statistical physics tools to compute this joint distribution. So this is the key idea. So for instance, so this is the problem. So we have a gas of particles with some interaction between them that depends on the joint distribution, and we have a wall. Okay, and we want to compute the partition function. So let's see what happens in the i.i.d. case. Why i.i.d. case is simple? Because when you have this factorization, P of x1, x2 just factorizes, then immediately you see that the energy, which is the minus of log P, is just a sum of minus of log P xi, which means that these particles this gas is a non-interacting gas. There's no interaction between the xi's. So it's a completely non-interacting gas. And therefore, obviously your partition function just factorizes into the partition function of each individual particle, and then we have all the nice results. Okay, but in the case of strongly interacting gas, where you cannot utilize this factorization property, but nevertheless, we have many techniques in statistical physics. I mean, you know that, which is, either it's, you can use exactly solvable models like Bethe answers or something, or you can use large N theory using saddle point method, or path integrals, mean field theory, anomalization group method, large deviation theory. We have many, many techniques in statistical physics to compute partition functions. Okay, and so this is the idea. So this is this is the main idea that we use to compute using techniques of statistical physics, the partition function, and thereby say something about these extreme value statistics of strongly correlated variables. Okay, so that's the key idea. So now what I'm going to do in the rest half an hour or something, that I want to tell you that there are essentially 4 different areas where we have applied this idea, this key idea of strongly correlated systems. So first one is the real mass transport models, and there's a condensation thing happens there, real space condensation, I explain. Then the Brownian motion or Lévy flights, random walks, active particles, random matrices, and lastly the stochastic search processes, which has applications in computer science. So of course I don't have each of these areas is a separate field on its own, so I won't have time to tell you in details. I just say a few words about each of these areas just to give you a general idea of what is the problem and what we do basically. So let me start with the first one, which is the mass transport models. Okay, real space condensation. What do I mean by that? So let me start with this, this very nice experiment which was done by Vandermeer et al. About second granular gas. So basically, what you have a some boxes which are in parallel like this. Okay, imagine that it's a periodic system, and there are these little blue balls which are just granular particles. You can think of as beach balls or something, and so they can. It's a gas of granular gas basically. They can move around these little balls. And you have these holes connect between 2 parallel walls, and they can go through, these balls can go through from one box to the another box through these holes, okay, in either way. So you have a mass transport basically. So transport, there's a transport phenomena. Particles can go from one box to another box, okay, through these holes. And what you do in this experiment, what they do is that they shake this, they vibrate this assembly of boxes with some rate and some frequency. And what they observe, without going into the details of the experiment, what they observe is that for some parameter space, by parameters I mean the frequency or the amplitude of the vibration. So what you find is that somehow these particles, many particles, they condense onto one single box. And this single box, the spontaneous symmetry the translational symmetry is spontaneously broken. And if thermodynamically large number of particles condense onto a single box. Okay, these are shown by the red here. Okay. So there are of course other particles around it, but a finite fraction of all the particles, they condense onto a single box. Okay, and the translational symmetry is spontaneously broken. Okay, so what has this got to do with the extreme value statistics? Because you immediately realize that if I want to now study that, for example, how many particles are there in the condensate? I just ask a simple question. Okay, so how do I go about it? So here basic degrees of freedom are the ni's, which are the analog of the x size that I was talking about before, time series. So ni is just the number of occupation number, that means number of particles in a box ith box. Okay, so I look at my time series n1, n2, n3, etc. The number of particles in each box, and then obviously the condensate. If there is a condensate, the number of particles in the condensate is just the maximum of this n1, n2, n3, nn. By definition, condensate is the one which has the maximum number of particles, obviously. So therefore, you see that this is an extreme value statistics problem. If I want to characterize the condensate, I need to know the distribution of the maximum of this n1, n2, n3, nn, right? So all I have to do now is that given if I know the underlying microscopic dynamics of these balls, how they go from one box to another box, what is the rate of mass transfer from box to box, then I should be able to, in principle, I should be able to compute the joint distribution of this n1, n2, n3, nn in the stationary state. And then from that, I want to compute this in the maximum of this using the ideas that I mentioned before. Okay, and so I won't go into details, but this is exactly what we pursued. So given the mass transfer rates, we can actually, for very different models, we can actually compute the joint distribution of the n1, n2, n3, nn. And of course, there is they are strongly correlated because there is a total number of particles is conserved here, then because it's a periodic system, so total number of particles is conserved. They go from one box to another, but the number of particles is conserved. Sum of the ni is fixed to be capital N. So that global constant already imposes some strong correlations between these ni's. But nevertheless, given the rate of transfers in various models, we can actually compute the joint distribution of the ni's in the stationary state, and from there we can compute the distribution of the maximum. So, example of strongly correlated variables, so you can compute things exactly. So I won't give you the details, but basically we can characterize the such a condensation in real space. So this was a joint work with many people. I mean, some of you are in the audience here, and then then this idea of real space condensation actually occurs in many other systems. For example, if you have in systems of diffusion, aggregation, fragmentation models, for example, if you have in the surface growth, where you're growing thin films of atoms or clusters of atoms grow, or the growth of polymer gels, formation of clouds. So all these things are basically examples of real space condensation. So the condensate is essentially the maximum of these NI observables. And you can actually use these ideas there to characterize the distribution of the particles in the condensate. Similarly, in traffic models, formation of a traffic jam. Traffic jam is just the analog of condensate, a big traffic jam. And you can look at for example, in growing networks. I mean, if you have growing networks, and then usually you have a hub like Google, for example, which has lots of links and connected to this node. And such a hub is what is called the giant component of a network. And again, you can analyze the distribution of the number of nodes in the giant component using these extreme value statistics. Then in the active particles, run-and-tumble particles, I'll talk about it a little bit later. And then you can have if you look at for a very large time, then you can have a very giant run. The run-and-tumble particles means that the particles which move in constant velocity in certain direction and then change velocities. So you can have a very large run of a single bacteria, and this is another example of a condensate. And finally, very recently, with Roberto Lévy and Stefano Ugini and Giacomo Gradenigo, we looked at the discrete nonlinear Schrodinger equation. And here you have actually localized wave functions which form. And these localized wave functions are again the examples of this kind of condensate, which is again examples of extreme value statistics. Okay, so this is the first subject, and let me now talk about just random walks and Lévy flights. Which of course most of you are familiar with. So just to give you an example, so if you just think of just a one-dimensional random walk, so you have one dimension, you have continuous space and discrete time, okay? And suppose that xi is the position of a random walker at step I. So xi evolves by a simple Markov process. So position at time I is the previous position plus a jump variable, noise. And these noise variables, they are independently drawn. Each time it draws a random number from some underlying distribution p of eta, starting from the origin. So it moves. The trajectory of the random walk is shown here. Okay. Now these eta i's, they can be, I mean, either noise distribution with a finite variance. So in that case, this will be a normal walk in the sense that large n limit, this will just converge to a Brownian motion. On the other hand, if the sigma square is not finite, the variance is not finite. For example, if you choose your noise distribution from a power law distribution for large eta, then this is called the Lévy flight, in which case it will not converge to Brownian motion, but it will remain very long jump process. This is called the Lévy flights. So this is a general random walk problem. And so here again, the variable xi's are strongly correlated, even though the noise variables are uncorrelated. Okay, the increments are uncorrelated, but you see the xi's are correlated because if you like the joint distribution of the xi variables, this is just the product of the eta I variables, but eta i's are xi plus 1 minus xi, right? So therefore, or sorry, it should be xi minus 1. And so therefore, so you see that xi's themselves don't factorize, even though eta is factorized. So xi is actually still strongly correlated here in this example. And you can ask, for example, what is the distribution of the maximum position, maximum displacement of the random walk? It's a very standard question which appears with many applications. So here, again, the key object is this object Q and W, which is the probability that the maximum is less than W. So which means that the probability that all the points of your trajectory of the walk stays below the level W, okay? So this is, then you see that this is also related to the famous problem of persistence or survival probability, or a first passage problem. So you're asking that you have a stochastic process and you're asking what is the probability that up to step n, this stochastic process stays below a certain level W, okay? So, and first passage, because the first time you cross this level, this is called the first passage problem. So first passage is related to just the just the derivative of the survival probability essentially. Okay, so when this process is just a Brownian motion, then of course it's quite easy to compute the survival probability just by using path integral Fokker-Planck method with the absorbing boundary condition here. But when you have a Lévy flights or other types of stochastic process, this is much harder to compute because the extreme value statistics of strongly correlated variable is hard to compute. Okay, but okay, over the last few years, at least for this problem, with the arbitrary noise distribution of a discrete time Lévy flight, so we were able to compute many of the objects, extreme value statistics, for example, the distribution of the maximum, or the order statistics, gap statistics, record statistics, etc. For 1D discrete time for arbitrary noise distribution. And it has many applications in fluctuating interfaces, disordered systems like CNI model, finance, ecology, and so on. So again, I'll not go into details of all this body of work. As I said, it's a field on its own, but just to tell you that this is an example of extreme statistics, and there are various collaborators with whom I've worked on this subject. And but this is just to give you an idea. So maybe I'll just spend a couple of slides just on a very recent related problem, which is about the active particles. So this is the extreme statistics for active particles. So as you know, the Brownian motion, which is shown in the left panel. So Brownian motion is just this yellow particle is like a pollen grain in a liquid like water or something. So this guy has no autonomous motion. Okay, so it moves because it collides randomly with the molecules surrounding it. The molecules are just moving around randomly, and once in a while they collide with this yellow particle, and the yellow particle moves because of its collision, because it's induced by the motion of the molecules around it. Okay, so this is our standard passive Brownian motion. Okay, in contrast, in active systems, for example, in E. coli bacteria are just bacteria which has a flagellar structure. So they have a tail which has a flagellar structure which gives it a directed motion. Okay, so it goes in the opposite direction of the tails. So what happens is the E. coli bacteria, when it's searching for food during the foraging period, it starts at some point in space, and then it chooses a random direction and a random velocity from some distribution, and it moves along that direction with that velocity up to a time which is exponentially distributed. Typically, it's called the run, and then at the end of this run, it reorients the velocity. It chooses a new velocity and a new direction, and then again it moves for an typically exponentially distributed time, and then again it tumbles. So this is called the tumbling. Okay, so it runs and tumbles, then runs, tumbles, and runs, tumbles, and so on. So here the motion, so the particle actually absorbs energy directly from the environment. There are no surrounding particles, so its motion is autonomous. It has its own directed motion, and it just moves around according to these dynamics. It chooses. So input here is the velocity distribution at each tumbling and the time period and the distribution of the time during each moves. So the run time distribution and the velocity distribution at each tumbling. So if you give me this, then I can draw the trajectory for you. And typically, if it is exponentially distributed runtime, so there is gamma inverse, which is which gamma is typically the inverse of the time scale, persistent time scale during which it runs. So this is called the tumbling rate. And so you give me this this simple model. So it's just a single particle. There is no surrounding medium, just a single particle, active particle. And you can ask various questions about it, extreme value statistics. For example, you can ask what is the maximum displacement along a particular direction, x direction, say, or you can ask what is the time at which the maximum occurs, and so on. So all these extreme questions, actually, you can solve it explicitly. And this was a sort of recent work with Francisco Mori, who is doing his PhD in our group, Pierre Dussal from École Normale, and Gregory Scher, who is my colleague here at LPTMS. And what he showed is that you can actually solve this, even though this is a strongly correlated example. You can solve this model explicitly. I'm not going into give you the details, and it has amazing universal features, meaning that it's independent of dimension D, it's independent of the velocity distribution W of V, and so on and so forth. So many interesting properties that you can actually derive for the extreme value statistics for these objects. Okay, so let me now very quickly tell you a little bit about random matrix theory. Again, I won't go into the details, just to give an overview. So I already mentioned about the random matrices. So essentially what we have is a Hermitian random matrix H, which models my Hamiltonian of a quantum system. And so all we are interested in the eigenvalues of this matrix, which are random variables. So basically you give me the distribution of the entries of this matrix H, and I want to calculate the distribution of the eigenvalues, and that will be the input for calculating further extreme observables. Okay, so fortunately for Gaussian unitary ensemble, the joint distribution of eigenvalues is well known from the work of Wigner and even people before that, and it's known that the joint distribution of eigenvalues, when you choose the entries from individual Gaussian distributions, is given by just a Gaussian factor here, e to the power minus summation lambda square. But then there is a product factor which makes the eigenvalues correlated. Okay, so this is lambda j minus lambda k square. So if you did not have this factor here, this van der Monde factor is called the van der Monde factor. So this van der Monde factor tells you that the eigenvalues repel each other, because the probability that two eigenvalues are very close to each other goes to 0 because of this factor here. So that means the eigenvalues repel each other. So if I did not have this factor, then of course this will be factorizing. So this will be i.i.d variables, it will be random energy model essentially. But because of this correlation here, we have strong correlations between the lambda j and lambda, all pair of eigenvalues, that makes the problem, strongly correlated. Okay, and so I'm not going to give you the derivation of this. This is the result, but take this as an input, and then we want to compute the distribution of the extreme. Okay, so you see that immediately what I was telling you, that this joint distribution, you can just raise this van der Monde term here as exponential, and then you can write this as e to the power minus some energy function. And what is this energy function? E of lambda I. So it has two parts. So one is this part, which is this, it's like sitting all the charged particles. Say lambda is the positions of your particles, and they are sitting in an external harmonic potential. So this is the potential energy term. Okay, and they are repelling each other by this log interaction. Log comes because you raise the van der Monde to the power something. So you see, this is a pairwise interaction. It's like a mean field model. Every particle is interacting with every other particle through this long range interaction. So it's a 1D mean field long range interacting system with a log repulsion. So these two energy terms, they compete with each other. So this guy is trying to push all the particles towards the center of your potential well by trying to minimize the energy. Whereas this guy tells you that you cannot come too close to each other. There is repulsion between pair particles. So as a result, the competition between the two terms, the eigenvalues, they settle down over a finite region of space with a density which is called the Wigner semicircle. But let me not get into the details. But basically, this is it. So we want to just, we have a gas of particles, as I said, with this energy, pairwise energy. And so if I want to calculate the distribution of the largest eigenvalue, or the minimum eigenvalue, which is the same distribution as the lambda mean, has the same ground state energy, which is the same as the lambda max because of symmetry. So all I have to do, as I told you before, that I have to just look at this gas of particles, but in the presence of a hard wall, W, because my cumulative distribution is at the probability that this Boltzmann weight, but restricted from minus infinity to W. So all we have is a strongly interacting long-range gas in the presence of a hard wall. And it turns out that you can actually solve this partition function. And this is known in the literature as Tracy-Widom distribution. This has created a lot of interest, recent interest. So these two gentlemen, Tracy and Widom, mathematicians, so they actually could derive this distribution of the lambda max. And it turns out that it has a scaling function, some function of W minus root 2. So, it has a mean value, which is root 2. and with width which is n to the power minus 2/3, and they couldn't compute the scaling function exactly, and this is a non-Gaussian function. It has a non-Gaussian tails, asymmetric. On one side it decays as exponential minus mod z cube, on the other side it goes like 3/2, and it turns out that although it was originally derived in the context of random matrix theory, this Tracy-Widom distribution was really ubiquitous, and it was found in many unrelated problems, from directed polymer, then growth models like in Kardar-Parisi-Zhang equation, sequence alignment in biological problems, large and gauge theory, liquid crystals, spin glasses, and many systems. And in fact, there are many experiments where this Tracy-Widom distribution was measured. Experiments in turbulent liquid crystals and coupled lasers, then disordered superconductors, and so on. And again, I don't have time to tell you about the details, but if you're interested, there are two nice popular articles on the ubiquity of Tracy-Widom distribution. So you see in this picture, this is from Quantum magazine. And it's related to many different problems, and why this Tracy-Widom distribution appears in different problems. So you can actually read these two articles if you are interested. And so one thing we looked at is going beyond Tracy-Widom. So Tracy-Widom describes the typical fluctuations of lambda max, which is of order n to the power minus 2/3. So you can ask, what happens if the fluctuations are very rare? That means if I'm looking for the distribution on a scale which is much bigger than this typical fluctuation n to the power minus 2/3, how do I describe these tails? Okay, so it turns out that, so here's the picture. So if I plot the PDF of lambda max versus lambda max, so there's a typical fluctuation of lambda max around its mean value, around this √2, which is of order n to the power minus 2/3, and this typical distribution is described by this Tracy-Widom distribution. But you can ask, what about the tails? Okay, and the large deviation tails on either side. Okay, so it turns out that the both left and large deviation tails are very different. In one side it goes like exponential minus n square of some function, and on the right side it goes like exponential minus n times some function. So in your picture of this gas in a wall, on the left side you're pushing the gas, on the right side you are sort of taking away the wall far away from the gas. So they are very different physics, and the pushed versus pulled gas. And what happens is that when you take the large n limit, as you increase n, you see this region here, the width is becoming narrower and narrower. So in the very large n limit, it almost becomes a kind of delta function. All your weight of the PDF is concentrated around the mean. And in that sense, what you see is that in the large n limit, it becomes a phase transition, which is that the left phase, left large deviation is like a free energy of the pushed gas, and the right large deviation is the free energy of a pulled gas, if you like. And these two phases, so they have these large deviation functions have the meaning of the free energy, and there's a discontinuity in the analytic properties of this free energy, and it's a third order discontinuity. Third derivative is discontinuous, and in that sense, this point here is like a critical point, okay, separating the two phases with free energies phi minus and phi plus. And so this is the meaning of the universality of the Tracy-Widom distribution. The reason why Tracy-Widom distribution is quite ubiquitous is because it's at the proximity of a critical point in the usual phase transitions and critical phenomena sense. So again, I'm not giving you the details. I mean, this is just roughly the idea, basically. I mean, that this is how we understand why is it so common, because it's actually proximity of a critical point. Okay. And so I didn't have time to give you the details of. There are many results which have been derived in this recently in physics and maths literature. And so with Gregory Sher, we wrote a sort of review on this third order phase transition and the large deviation functions of this largest eigenvalue of a random matrix. Interested, you can find many of these articles in this review article. Okay, so finally, let me just mention one word about the stochastic search process. So, which is the fourth topic. So search processes are ubiquitous in nature, in data search, like in Google, or protein searching for a binding site on a DNA chain, or animal searching for food, foraging. And so this is a very, very ubiquitous process, stochastic process in nature, search processes. And in search processes, always people are looking for optimizing search processes. Which is the strategy? Which is the optimal strategy? That means you want to find your target, whatever you are looking for, in the minimal time. So you want to optimize your search strategy. Now, optimizing a search strategy means that basic principle is that you want to minimize some appropriate cost function. So you see the minimization. Minimization means basically, again, you are looking for the extreme value of some cost function. So that's how the extreme value statistics comes in these kind of optimization problems and the search processes problems. And one particular example which you have studied in quite detail in recent years is what is called the stochastic resetting, which means that if you do random search, for example, just by diffusion, if you are looking for animal searching for food just by random diffusion, then it might take a very, very long time. But it turns out that once in a while, if you reset, that means you go back to your initial starting point with some rate and restart the process, then it turns out that this is a much more efficient strategy. That means you can find your target in a much less time. And the basic idea is that when you reset, you actually explore some new paths. So as a result, there's a higher probability of finding the target instead of keep on searching futilely your target. If you restart your process, and it's not just a diffusion, it's actually much more general. It turns out that many of this optimization process is actually a very efficient thing, that you just once in a while you just restart your for example, if you're writing a computer algorithm to search something, it's better to reset once in a while and restart the process, and it makes the process much more efficient. And again, in the context of, for example, animals searching for food, so here the cost function is as a mean first passage time to find your food or target, and you want to minimize this mean first passage time. That means you want to ask what is this resetting rate R, which will minimize this mean first passage time. And again, you see that obviously extreme value statistics plays a very crucial role here, and typically these problems are again problems of extreme statistics of strongly correlated variables. Okay, so again, I didn't have much time to talk about it, but again, for the details, you can find the review article that we recently wrote with Martin Evans and Gregory Sher, which is this year only. So let me just then summarize essentially. So the summary is that, main message you can take off is that extreme value statistics, there are two steps. So one is the step one, which is the modeling. So you go to your data and you take any time series, and you have to first estimate what is the joint distribution. Okay, so this is part of your modeling. So, and once you have that, then the step two is the computation part. That means given this joint distribution, I want to calculate the distribution, for example, of the several extreme observables, for example, X max, which as I said, is just a probability that it's just a multiple integral, which is minus infinity W. And so it's just a partition function of a strongly interacting gas. And the main idea is that using statistical physics tools, we have many techniques at our disposal, which you can use to compute this distribution of X max. And the final goal is to understand the strongly correlated variables, and in particular the different university classes. They're not there yet, and we want to at the moment we're studying different models and different systems, and the ideal goal would be to understand like in the RG sense, are there fixed point distributions for strongly correlated variables, or what can we say, is there any general theory or not? These are the sort of open questions. And so the conclusion is that, I find it a very exciting and rapidly evolving field of research. And as I said, it connects up so many different fields. On one side, you have statistics, geology, finance, epidemiology, engineering. You saw many applications there. On the other side, being physicist, we have statistical physics, disordered systems, random matrix theory, Coulomb gas, gauge theory, cold atoms. We have quite a lot on the cold atom systems also, and all the way in mathematics to number theory and so on. And so we wrote recently, again, it's a publicity, a sort of pedagogical review on this extreme value statistics of correlated random variables with Gregory Sher and Arnaud Paul, and it appeared in this year physics report. So if you're interested, you can have a look at that. So last but not least, let me acknowledge all my collaborators. there have been many students. The red ones are the current students, and they are former students and postdocs, and there are many collaborators at LPTMS. So I thank them all, and also I have many collaborators outside LPTMS. And I'm sorry to present the big names like in a random list like this, but all of them have made many important contributions in the development of this field. So I thank all of them, and I thank you all for listening. Thank you very much.
Thank you, Satya.
Thank you, Satya, for the very interesting talk. So now we have some time for questions, if there are any. Any question?
I have a question.
Yes, please.
Federico.
Mm-hmm.
Hi.
Yeah,
hi, Satya.
Hi.
Thanks. Hi.
Hi.
Nice talk. I have a general question about what do we know about the extreme statistics of eigenvalues of matrices which are not dense? In the sense that,
matrices, yes. Yeah. This
so
is
how much we can go beyond the matrices?
Yeah, of course. This is a question which I've been interested for a very long time. The problem with sparse matrices, as you know, I mean, we don't really know the joint distribution of the eigenvalues. Okay, so this is one of the problems. So you can, of course, calculate the average density of states, but using resolvent methods or whatever. But to compute the extreme statistics, I mean, lambda max is very hard in general. So yeah, I mean. Okay, it's a hard problem. So
let me ask you a question about an intermediate case. Suppose that you don't want to really have a sparse matrix, but slightly diluted matrix.
Okay.
So between having all elements non-zero and having only a finite number of elements per row different from zero, you may have in between a lot of situations. So my question is, what is the technical hardness, and when do you start having problems? So can you dilute a little bit and still works? Because maybe you can use law of large numbers. So what do you require to get an analytical result?
Yeah. So I think one thing you can probably do is if you make this perturbation, for example, just by a rank 1 perturbation. Okay. So you take your matrix and you just make a small perturbation with the rank 1. Just one element of the diagonal is non-zero, and then and hope that that you can extend it to higher rank perturbations. I mean, I don't know if it has been systematically done yet or not, but certainly rank 1 perturbation you can do. I mean, and in fact, this was some work by also Giulio Biroli and the Bike and other people, Benarus and Pesce. They looked at the rank 1 perturbation, the spiked matrices, but I don't know if you can go beyond. I mean, how difficult it is to go beyond rank 1 perturbation, something, in fact. So that would be interesting to pursue, certainly. Yes.
Okay. So not very much is known.
Not very much is
known. It's worth studying.
Yes, absolutely. No, I agree totally.
Okay, thanks.
Yeah.
May I make a question for Satya?
Yes, please.
Look, I was just on the line that Federico was raising now. You told us that the main message that you provided in this talk is that you have 2 steps, and the first step is providing a joint probability distribution. So having in mind a model that allows you to enter the game of extreme statistics. statistics. But the problem is that it's clear that you can really face a lot of situations well beyond the random matrix approximation that may pertain some very interesting applications. I can imagine that if in epidemics, or I don't know, as you mentioned, in other fields, that's the real problem in some sense.
Yes, absolutely. No. As I said, there's two parts. I mean, one part is the real modeling. Okay, that's really the very important part. And then second part is the computation part, where, you know, given the joint distribution, it's not always easy to compute the extreme statistics, basically, right?
Yeah, but we have not
mathematical problem,
telling you that if this is really feasible. I mean, suppose you build up a reasonable joint probability distribution of some phenomenon that you want to describe.
Yes.
That's not sure that you will be able really to perform the computation. So you have
absolutely, yes, that's right. No, it's not sure. No, that's a hard. In fact, I mean, there are examples, you know, where you know the joint distribution, but it's not easy to compute. I mean, you know, for example, I mean, just to give an example, I mean, if you just take the same gas, instead of log correlation between, instead of logarithmic interaction, if you make, let's say, 1 over xi minus xj to the power some alpha. Okay.
Yeah, in that case,
then we don't know anything about it, except for alpha equal to 0 and -1. We don't know really anything about the distribution of the extreme.
So, seen from another point of view, the main message is that there is a lot of things to do.
Absolutely. I mean, no, there's a lot of things which are open problems. I mean, completely. I mean, both the, you know, in the modeling part as well as in the, you know, in the computation part, basically.
Yeah. So it's good news for young people. So young people can really
absolutely. They should all come and work on extreme value statistics.
Yeah. Okay. This is advertisement. So thank you, Satya, again.
Thank you. Yeah. Okay.
Any other questions? Okay, so if there are no more questions, we can thank again Satya for the very nice talk. Thank you.
Yeah, thank you. Thank you. Yeah. Thank you. Okay, thanks.